right. Welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg. Still in Luxembourg, but you might be already aware we're changing a little bit. And I'll be telling all about it on social media, so you can check out what's happening, how we're coming back to roots and all that. But still, as I said, in Luxembourg today, which means we are proudly powered by Research Luxembourg and recording at the Media Center of the University of Luxembourg. And one more Luxembourg, because we have a Luxembourg-based researcher, and this means our guest today is Dr. Karl Shneider, who is Associate Researcher at S&T at the University of Luxembourg, specializing in space weather. Karl also works on an industrial project with Mission Space. Karl, thank you so much for coming today.
Thank you for having me, Hannah. It's really awesome to be here.
So we start with what you specialize in. So the big definition, space weather. What is that?
Well, space weather encompasses a broad range of phenomena. If one can sort of summarize it in a nutshell, it's events coming from our sun that affect human life and technology on Earth, and also technology that we've developed in space, such as satellites, and possible future missions to Mars and the Moon and so forth.
But I wake up in the morning and I check the Earth weather. I don't go and check the space weather. So it does not affect me personally, does it? It's just the space people somewhere there.
So actually, it does have effects in terms of auroras. So it can create these beautiful light shows. But on a more serious note, it can disrupt GPS and GNSS signals, cause radio blackouts, cause large uncertainties in positioning systems, so that endangers flights, also vehicles that depend on GNSS. Drilling operations are affected. Entire national power grids are affected. Also, undersea cables also have currents induced, and that can rupture. Pipelines under the oceans or under the ground can cause accidents that have occurred in early 20th century, like fires on telegraphs. There are actually space weather advisories, just like for terrestrial weather. I think it's really just a matter of being aware that there is also such advisories, especially there is one coming from Belgium. I think that serves Europe. So that's from the Space Pole, I believe, or there's another organization. The KMI provides like a live forecast of what's happening in the sun. And also NOAA in the US with the Space Weather Prediction Center. NOAA has a hurricane monitoring system where anyone in the world can check, what is their predicted strength, predicted path. Analogously, there is also for geomagnetic storms. What is their strength? Is it G1 very low or G5 the strongest? Can auroras be seen? Your podcast today actually corresponds to a major, very large CME, coronal mass ejection, that has impacted Earth, actually, I think yesterday. They didn't know what was the magnetic field configuration of that magnetic cloud. So there was a big chance to see auroras quite at low latitudes, but the magnetic field configuration was such that it didn't cause such a powerful storm as it could have.
We need to add here that, of course, we are recording the podcast earlier. So when you're listening to it, when it goes live, then maybe there is another phenomenon that is just happening, but not the one that we are at today. And we're recording on the 3rd of September. So you can check what was happening then. Exactly. Well, that's just a point. So, I have a problem also with the Earth weather. So let's unwrap this first. It's a lot of calculations, a lot of people involved, a lot of apps, a lot of programs you can watch. And the accuracy is sometimes great, sometimes not so great. Depends, obviously, on so many different factors. How accurate are we with the space weather?
That's a great question. Well, for terrestrial weather, as you said, we have dedicated satellites that use radar, that use other instruments to scan the Earth and look at conditions in the atmosphere, in the troposphere, look at hurricane formations, look at areas of low pressure systems, wind systems, ocean currents. So these phenomena are very well studied and studied at high resolution. There are large numerical simulations, large supercomputers dedicated to modeling and simulating terrestrial weather. Now, for space weather, it's hard. It's a hard problem because data is sparse. So you have a much larger area to cover. Earth is at 150 million kilometers from the sun. Most of the satellites that are observing the sun are at Lagrange point 1, which is a stable gravitational point, which is located at 1.5 million kilometers, so just 1% of the distance away from the sun. Well, actually, if one would go from there to the sun, 1% of that distance, 1.5 million kilometers instead of 150 million kilometers. And so there's a suite of instruments that sits there. Some of it sits within the magnetosphere. So Earth has this magnetic shield. Actually, thanks to Earth having a magnetic field, it deflects all the radiation and solar storms that come our way. So the magnetic field really is the force that is the most relevant in space weather. It's also what drives activity in the sun. So thanks to magnetism, the sun forms these sunspots, which are areas of high magnetic fields.
I have to interrupt you here. You mean the magnetic field of the sun, not the magnetic field of Earth.
So magnetic fields are ubiquitous. There's a book by Brian Gensler. If it's okay, I'll just mention some references. Maybe your
listeners are already used to this. There's always our show notes, and we share all the links as well. Great. So if you want to read up or you didn't understand the name or whatever, it will be all in the show notes.
Oh, perfect. Yeah, there's a great book by Carl Schreiber also. Yeah, so indeed, the magnetic field is ubiquitous. So it was there with the birth of the universe, and our sun has a magnetic field. And that magnetic field drives activity on the sun at enormously different scales. So you have like nanoflaring events, kilometer-sized convection cells, which means this plasma that literally looks like a cell of a living organism in a way. It forms these cell patterns. And that's where convection happens. And when you have rising magnetic flux tubes that rise up because of magnetic buoyancy, they prevent this convection. And so it causes a cooling in the plasma, making the spots because they are darker and also colder, I think, with respect to the other areas of the sun.
So these are not holes? Because they look for a lay perspective, it's a kind of a black thing.
There are coronal holes also. That's where you have, let's say, the fast solar wind. You have slow and fast solar wind that comes. Basically, you call them holes.
But here we're talking about plasma, going back to the plasma, right? Sorry.
The sun is a giant plasma ball. It's a nuclear fusion reactor. It's giving us heat, light, warmth, radiation. Interestingly, it also forms a huge bubble that encloses our entire solar system. So Voyager 2 has left the heliosphere like a few years ago, I think, after like 33 years of travel. And that heliosphere actually shields our solar system from very high energy galactic rays. So the sun's magnetic field both shields our solar system, but also causes a lot of these coronal mass ejections, solar flares, which pose a danger for human life and also technology, the modern technology that we've all come to depend on satellites, space missions, 1972, Apollo. Luckily, their schedule was several months apart, so that missed the storm that occurred in July, which would have given the lethal radiation to astronauts. So luckily for the space mission, that was avoided.
And we didn't know it at that time.
No, so it wasn't known that 1972 that there would be a solar storm. Also, 1972, there was an incident where during the Korean War, a lot of U.S. submarine and ship mines all of a sudden blew up in the ocean, and people thought it was someone had triggered that explosion, but that was caused actually by the arrival of the same July massive solar storm. And Dolores Knipp is another reference. Dolores Knipp is one of the key people in space weather and also historical space weather events. And she has written really like the Bible of space weather. And so if anyone's interested, it's a very, very thick book on space weather. And Dolores Knipp has been a professor in Colorado for the, U.S. Air Force, if I'm not mistaken. So she's the world expert on space weather. And there are a lot of other historical interesting...
You will tell me about it soon, but I have to circle back. I have to circle back a lot because I asked you actually, I don't know if you remember, how much can we actually predict the weather? But before, maybe that was too early to ask because true, we didn't really discuss what we mean when we say space weather. You mentioned a little bit the sun's magnetic field and the fact that the Earth has a magnetic field that shields us a little bit, right? So first of all, before you tell me a little bit more, does it mean that Earth is really special? There's no magnetic field on the moon or Mars?
That's an interesting point because actually the moon is both unshielded, so it doesn't have its own liquid core. So this liquid iron core, which actually the movement of this liquid metal, because it has electrons, it induces a magnetic field. Mars it's believed, I think, that the liquid metal core has frozen. So Mars no longer has a global magnetic field. It has local patches of magnetic field. The moon has local patches of magnetic field, but that's more from impacts of meteors or even asteroids. But Earth has a living, evolving magnetic field, a magnetic field that changes over time. There also have been periods like 41,000 years ago. There was this weakening of the magnetic field. That happened 41,000 years ago. So there are like geological times of 100,000 to 200,000 years, where the Earth's magnetic field decreases or even disappears for a few days. This Lunchamps excursion, which happened 41,000 years ago, it's thought influenced the dying of the Neanderthals, because Neanderthals were not easily able to adapt, as were Homo sapiens, to increased radiation. So that increased radiation would have caused skin cancer, burns. It would have been very difficult to be outside for extended periods. So Homo sapiens had developed clothing. They used ochre for shielding their skin. That would have given them a significant survival advantage. So space weather also could have influenced evolution on our planet directly in terms of Homo sapiens and Neanderthals.
That's a fascinating possibility, right? We're jumping a lot and going different places. But you want to mention something more? I interrupted you.
Sorry. So just to go back. Sorry, I keep circling, but to go back to your question about magnetic fields. So space weather has been with us ever since the sun formed and the Earth formed. So the sun formed 4.6 billion years ago. Earth formed 4.54 billion years ago. There was the young sun. The young sun was probably flaring much more stronger flares that we luckily haven't seen in our time. What's interesting is that because the young sun was probably very active, the moon would have recorded that activity. So there is a field also of solar space weather paleontology. By studying the composition of certain isotopes in the moon, one can prove or disprove whether the young sun was more active or not. So the moon can be used to study the sun. There's the quiz question that you're the quiz master. So the quiz question, when we'll get to it, is along these lines because, space weather has been with us ever since humanity has been here. And the question is, when is the earliest recording of a geomagnetic storm or an aurora by humans? And interestingly enough, there have been, for instance, Aztec, Mayan civilizations, but it is not yet known whether they witnessed it or not because of their geographic location on Earth.
So the answer to the question is not 100%. We are not 100% sure whether it was.
No. So that's why.
Let's do the question because people now got interested.
Okay,
so yes,
sorry.
What are we talking about? We're talking about your T-shirt because listeners, you can't see, but Carl is wearing today a Aurora Borealis T-shirt, perfect T-shirt for the question and our discussion.
Yes, and if I may mention, this T-shirt is from Finland, so they are talking about Aurora Borealis. There's also Aurora Australis, which can be seen in the south, so Australia. So I think if someone goes to New Zealand or Australia, maybe one can get also
for sure
Aurora T-shirt, but Aurora
with a kiwi maybe.
With a kiwi, yes.
So anyway, question please.
Yes. So the question is the following: what is presently? So I'm phrasing this carefully. What is presently the earliest known recording of an aurora? And an aurora is a manifestation of a geomagnetic storm. So is it 10th century before Common Era, BCE? Is it 6th century before Common Era, BCE? Is it 17th century in our present era? Or is it mid-19th century in our present era?
Great. So now we have it out of the door. We can focus on other things. But for listeners, remember, if you're interested, the answer at the end of the podcast. So yes, I will try to circle back again. I don't know to which point, but magnetic fields. I wanted to ask you one more thing before you tell me more. So basically what we're talking about is that we have the Earth magnetic field, we have the sun's magnetic field, and all the stars in general have magnetic fields.
That's a wonderful point. I would reference Brian Gensler's work, which is wonderful because it describes magnetic fields on ginormous scales and also on the smallest scales. Basically, the message is the magnetic fields are ubiquitous. So magnetic fields exist on galactic scales. They exist on planetary scales. And they're continuous. So the sun's magnetic field connects with the Earth's magnetic field. That magnetic field of the sun permeates our solar system. That extends into our galactic magnetic field that follows our spiral arms of the galaxy. And that magnetic field also then just goes to the in-between galactic regions and also to other galaxies. So it's an infinite magnetic landscape.
But we know that Mars doesn't have it.
So Mars doesn't have an internal magnetic field.
Okay.
Sorry, let me clarify. So some planets have internal magnetic fields which shield them. And others, like Mars, may have had. Probably it did have because it would have had a molten core that was rotating and moving. Now it's frozen, I think. So that causes the magnetic field to dissipate. The magnetic fields would dissipate, I think, on scales of several millions of years, if not for the dynamo action. That's why it's necessary to have the movement of this liquid metal that carries these free electrons, and this electric field which induces the magnetic field. So basically the same way a bike, when one puts a dynamo mechanism, the light comes on, because the wheel is recharging the dynamo. Similarly, there's the alpha-omega dynamo or other types of dynamos in stars and in planets which regenerate the magnetic field. Otherwise, it would just die off. So planets that do have a magnetic field, it shields their atmospheres. For instance, there are other exoplanets around their host stars where their host stars, very strong solar flares have been observed. These red dwarfs, I think, that are smaller suns, but can have also very powerful solar flares. And those solar flares just strip the entire atmosphere from those planets. So life as we know it cannot exist there. Luckily for us, Earth has a magnetic field, which is like an onion. When the sun is cranky and it's active, because it has this 11-year cycle where it sort of wakes up, becomes cranky, you have these active regions that form, which can look ominous. Well, this goes back to this Carrington event, 1859, where Sir Carrington made a drawing of this very large complex, it's called, this active regions. And the size of those were like a number of Earths across, so a number of Earths could fit inside. Given that our sun is also 109 Earths across, our star is massive. And actually, the field of space weather is kind of philosophically also interesting because we're actually talking about the activity of our nearest star, which we call the sun. And we're actually able to have computer simulations and to predict and to model, also using helioseismology, to see what's on the other side of the sun, because the sun is rotating every 27 days. We don't see what's on the other side until it turns toward us. But using helioseismology, so actually quakes on the sun, we can map kind of what's happening. There are missions that look at the limb. So the limb is, as the sun is turning, like, will there be anything ominous that's there? Because if there is, there's a chance that there would be a coronal mass ejection, which is very wide in extent. And the analogy that's given is basically like the Earth is a pebble on the beach, and you all of a sudden have this tsunami wave, this giant tsunami wave that just washes over the Earth. And because of Earth's magnetic field, most of this kind of washes around. But if the coronal mass ejection or the solar flare has a magnetic field configuration which is pointing opposite to the Earth's magnetic field configuration, it's able to penetrate, to start kind of cutting through this Earth's protective shield. And the vulnerable areas are the poles. Because of the solar wind that's coming from the sun continuously, it compresses an otherwise dipole field. So a dipole field, as you may know, is like coming out from the North Pole magnetic lines. It's like a bar magnet. You have field lines coming from the north, from the south. The north and south magnetic fields are opposite to the geographic north and south. And the magnetic field can also flip. So those are the days when every 100,000 years, 200,000 years, or during this lunch hop excursion where the magnetic field all of a sudden weakens, and then we're all of a sudden at the mercy of space, of radiation in space. And that harsh environment is what our satellites are exposed to. So GEO satellites have radiation-hardened shielding, but LEO satellites are protected by our atmosphere, which is further able to absorb, let's say, this radiation. But in case of strong geomagnetic storms, it's also exposed to a lot of radiation, like over the South Atlantic anomaly, which is this large region, which is basically an exposed area. Yes, so going back, the solar wind compresses the dipole field, and it extends it on the night side of the Earth. So basically it looks like a spider, like a large spider web. And speaking of the moon is unshielded, but it's by itself. But then it also enters into this extended field. So then it is shielded. So it's both shielded and unshielded depending on where it is on its orbit. So the electrons that come in on the day side, which didn't cut through the magnetic field, they wash over and come to the night side. But then the field lines, the magnetic field lines that are on the night side it's called reconnect. So they can snap and then topologically reconfigure. And then those electrons that are there all of a sudden spiral back in several days later after a storm occurred, and they spiral into the poles. And depending on the strength of the geomagnetic storm, depending on the energy that's injected, those electrons can go further south or further north. If further north if they come from the South Pole, or further south if they come from the North Pole. And that's why people can see auroras at lower latitudes. So that's why in Luxembourg, we had several months ago, like this reddish light, so the aurora borealis. Also, during very intense geomagnetic storm periods, like during the Carrington event, people could see the auroras as far down south as Mexico in broad daylight. And that's why people centuries ago, all of a sudden they are outside in the daytime and all of a sudden they see these red, green, blue lights during daytime. And for them, what is happening? Like, it must be so both beautiful, but also kind of mysterious. Maybe with their mythology, they try to explain, are the gods angry or have the gods given a gift for these mythological beings? Are there dragons? Are there, what is happening? Because this is definitely out of the ordinary. Are the heavens crashing? What is going on?
From a space weather expert perspective, is it normal that it's happening or should we be worried? I mean, it's meaning aurora reaching other sides than just the poles.
In 1859, when this great Carrington storm occurred, we didn't have the technology we have now. So we didn't have any satellite assets in space, but we did have telegraph wires.
Yeah, telegrams
yes, exactly. And telegraph wires.
Yes.
And many telegraph wires caught fire in October 1st, 1859, when the solar storm arrived. And also the people,
the operators,
thank you, who were giving the Morse code, they got electric shocks from the board. So that was a very charged event. These events also, like in 1921, there was a very big fire in New York at the railway station because the railway got induced currents, and that caused a big fire in the station. That station burned down. There were also other events. So like we mentioned during the Korean War, 1972, there was even a false nuclear alert. So in 1967, a geomagnetic storm caused the false alert that the USSR had fired warheads, and there was only half an hour to respond. And luckily, that day, a scientist was able to quickly analyze and determine that actually this was space weather caused and was not a real threat. But it came close to a nuclear war in 1967.
I'm asking about the normal to say,
yes.
if it's going to be more often happening, not necessarily whether this is a threat for us, because as you're saying, we're definitely more based on technology that is going to get destroyed if something serious happens, but more about, will it be happening more often, or is just once in some time that we can expect such changes?
So there's a granularity to the answer. So about every 60 years, there's expected to be like quite a strong event. A Carrington event was maybe one in 100, one in 200 years, maybe. This I'm quoting, I'm not exactly sure on the frequency, but Carrington level event is expected to happen, I guess, maybe every century or so, or every 2 centuries, let's say. These effects are very costly, so they would result in trillions of euros in damage. For vulnerable power grids, they would basically shut down the power grid, like in the US or Canada. Like in 1989, there was the Quebec power outage. So within 90 seconds, I think 6 million people lost power because of a geomagnetic storm. Transformers burned down also in New Zealand, in Australia. What's dangerous is that for GPS, GNSS, if that goes out, power goes out, one cannot fly, one cannot drive, internet is out, there's no banking, nothing that depends on satellite. So data centers would be affected by glitches. So our modern way of life would be severely affected, and it might kind of lapse back several hundred years for a short period of time. So there is that danger. That's why space weather entered officially into policy almost 3,000 years after it was first recorded. I don't know if I should perhaps go into that.
We will uncover it. Don't worry. I know you can't wait to tell more, but it will be there. Okay, one thing, of course, some of the listeners might be wondering, just like with hurricanes or any other extreme weather events, can we prepare for this? Let's leave the prediction aside. Let's say we are sure a very, very super storm, serious storm is coming. Can we shield ourselves or not really?
There are a lot of research going into predicting coronal mass ejections, let's say several days ahead of time. Now also research on predicting solar flares, but solar flares arrive very fast. So for instance, light travels 8 minutes from the sun to the earth. Heavier ions, nuclei, arrive 20 minutes later. Also solar flares, I think perhaps within that time frame, maybe 1 hour, half an hour. Coronal mass ejections arrive 2 to 3, 4 days later. Very fast events, like very fast solar wind, can travel at 1,000 kilometers per second. So that's why it takes 2 days, 14 hours, the fastest, I think, or 12 hours, or around there. That's the fastest arrival time. So solar flares, the heads up would be very short. Probably some satellite operators might be able to shut off some satellites, or at least lower their orbits, but that's very expensive, or change their orbits. For coronal mass ejections, with a few days heads up, the power grid can be rerouted. Airlines could adjust their schedule. People can be warned. So there are these systems in place like Pegasus for Europe, which is a system that monitors radiation levels in aircraft for pilots, for civilians. The Pegasus issues the same way weather advisories are issued. It issues space weather advisories with codes, so the airlines and pilots can assess the danger. There are active warning services in place, just as for tsunamis, just as for earthquakes, for volcanic eruptions. Space weather is also in the UK, it's listed as one of the critical threats to life and infrastructure and space assets.
So it's not about creating an additional magnetic field to shield ourselves. It's rather, as you're saying, shutting down the equipment, let's say satellites, or not flying, I don't know.
No, so luckily we're inside Earth's magnetic fields. There are satellites that monitor, like Stereo, that monitor the sun that are outside Earth's magnetic field. So like July 2012, there was a very large event that missed the Earth by 9 days. So if the Earth were 9 days earlier in its path, it would have been a direct hit. But the Stereo satellites were directly hit by that. So, they got a lot of radiation. Luckily, they're still working. They're designed to withstand very harsh conditions. We have like the Parker Solar Probe, which has come to 6 million kilometers from the sun. It's the closest object made by humankind that has come closest to the sun. It's also the fastest object because I think it has flown at 480,000 kilometers per hour, I think. So it's also now the record for the fastest human object made. And there are ground observations, satellite observations. The earliest observations were in 1610, when Galileo actually and a few other scientists observed sunspots for the first time. And Galileo was the one who proved that sunspots were not planets transiting the surface of the sun, but rather innate to the sun itself. And he proved that in a very elegant geometric way. Ever since the early 20th century, with new technology, people have been aware of space weather. The term space weather itself, I think, was coined in the 50s, but it took to the 1990s for space weather to actually be actively considered as something that is relevant for space assets. And in 2010 is when space weather officially was adopted and Swarm. Swarm was formed in order to actively study the sun and inform the government on space weather. And that formed in 2014. UN and the World Meteorological Organization in 2010 adopted measures of space weather as well. So it took almost 3,000 years after the first observation of an aurora, which occurred in the 10th century.
You have to solve it. I can see it.
Sorry. Okay. So sorry, but
it's all right. We're solving it now. It's all my planning here is just not working. Okay. Yes. Tell me, when was it? No, you can say it. Absolutely.
Sorry. So it used to be thought that the Babylonians were the first because there was a record of a great aurora in 576 BCE. But now they've discovered that in the 10th century BCE, the Chinese scientists recorded a mention of a 5-colored light in an ancient text, the Bamboo Annals, and that's from 977 BCE. So it's quite possible that there might be even perhaps earlier recordings. But yeah, 1610 is when Galileo and other scientists observed sunspots, and 1859 is the Carrington event.
That's a long time. Amazing. So space weather is Earth-centric.
So space weather as a term applies to any activity that is caused by the magnetic field of the host star of its host solar system and the coronal mass ejections, solar flares, solar energetic particles, other radiation that impinges upon the planets that are gravitationally bound to the star. Okay. So space weather is a universal phenomenon. It's just space weather for us is like we call the sun, which is a star, the sun. Space weather was coined. There used to be some other names for space weather.
I'm asking, you know why I'm asking? Because a couple of months ago, listeners, do check this episode out. I will also share a link in the show notes. I talked to Professor Christiane Helling, and we were talking about exoplanets, and we were talking about cloud formation on exoplanets. And I started thinking, again, terrestrial weather, clouds. Cloud formation should be space weather.
In fact, auroras were observed, I think, on Uranus.
Okay, but that's
and on Mars
still
also,
what we mean with space weather, as you're saying, is the the activity of the star. So in this case, our sun, that is always the one. We're not interested in, I don't know, storms on some exoplanet. That's not space weather anymore.
Well, so there's operational space weather. Operational space weather is exactly like in defense and preparedness of Earth-based systems. But there's also space weather for, let's say, for future planetary missions, for Moon, for Mars. Actually, when the coronal mass ejection passes, it also acts it causes a decrease in the galactic cosmic rays. So it itself shields. It's called the Forbush effect. So that was noticed actually from measurements of a satellite on Mars, that the galactic cosmic rays dropped because of the coronal mass ejection coming through. So this wave washes over quite a number of planets as it passes through our solar system. So space weather is, actually there are calls for space weather monitoring on the Moon, for Mars. Let's say ESA and NASA are going to send missions to the moons of Saturn, Enceladus. Well, that's still within our solar system. But I think people are also interested in habitability. And solar flares are a major part of habitability because they are single-handedly able to wipe out the atmospheres of planets. So even if a planet is within the Goldilocks zone where life can be, one also needs to model, is it a very young star? What is the magnetic activity on the star? Is it causing these huge solar flares that can easily destroy, basically make life very difficult as we know it to form on that planet or not? So perhaps space weather has also had a hand in seeding life somehow.
Possible, absolutely. Listen, Carl, I think after a couple of minutes of discussing, you've had your warm-up, so now you can actually tell our listeners a few definitions as well, because we're missing some things, because we were discussing some of the important phenomena on the sun or other stars, but I don't have a feeling we really told listeners what they mean. So we did talk about sunspots. I think that's clear for now. But first of all, solar wind. What is solar wind?
Yes, so solar winds are electrons and photons that are coming from the sun. So photons take about, let's say, 4,000 years to go from the core of the sun because of Brownian motion and to escape all the different layers of the sun. So to make it out from the photosphere to the chromosphere and out of the corona. There are a lot of electrons. There's plasma that is being lifted by these magnetic fields. It looks like if you go swimming, you have these noodles. It's like a big noodle. That's like on a rubber band that's kind of been ejected, and the magnetic field lines are stretched out. So this noodle cloud is coming out, but it's pulling the magnetic field lines of the sun with it. And then it's coming past Earth, and then those magnetic field lines are reconnecting with some of the field lines from Earth. So the topology is changing. So it's like plucking a violin or plucking strings, but these strings are dynamic, so they can just reconnect.
Now I wish we had video. I mean, this was very interesting, listeners.
Okay.
So we'll try to share some videos with you also in the show notes so you can see what Carl was actually showing with his hands. But I got it.
So the MMS
and I
mission,
hope you did as well. And you said that's from the sun to the Earth, that's about 2 days until the solar wind arrives.
So the sun is 150 million kilometers away. For a photon, it takes 8 minutes. For fast solar wind, it could take 3 days. For a coronal mass ejection, it could take 2 days. It depends on the initial conditions of the phenomenon that's coming our way.
Of course, but
solar flares are faster, 20 minutes.
Yeah, you're mixing in other definitions. Just wait a second. We have winds. We move on. What are flares? What are solar flares?
Flares. So flares are these very bright ejecta. They're not very wide in angular extent as coronal mass ejections are, but they're very powerful bursts of energy and radiation. They come in different classes like C-class, M-class, and X-class. X-class flares are the most powerful flares. In 1859, Carrington, he saw a very bright flash. And I think he's the first to actually observe a flare, because Galileo in 1610, he observed sunspots, but he didn't see any bright flash, at least not that we know of. Carrington actually saw a bright flash, and then 2 days later, there was a severe geomagnetic storm. And then these two things were put together, like, hey, wait a minute, maybe these ominous complexes that I saw in this bright flash, 2 days later, there's a very strong geomagnetic storm. The telegraph wires are on fire. Like, there's a correlation here. Like, it's not just...
Before, sorry. So solar flares cause geomagnetic storms.
So the arrival of a solar flare, the arrival of a coronal mass ejection, because of the magnetic field that's inside, that's frozen into the cloud or contained in the solar flare, if it's in the configuration that allows it to snap away at Earth's magnetic field, it can deposit the energy that's contained within it. So it can deposit these very high energy particles, these very high energy electrons, these nuclei. And those are the radioactive particles that collide with atomic oxygen, with atomic nitrogen, that give us the auroras, the different colors, the red, pink, blue. And those are the same radioactive particles that affect airlines, that can give a dose of radiation. And also they can cause the Van Allen radiation belts to puff up. So there's a region around Earth, because of the magnetic field, that traps a lot of these particles. So they're just there, they're just trapped, and they're called the Van Allen radiation belts, and they get puffed up. So there can be a third belt that can form when a large coronal mass ejection comes in and deposits this energy. Also,
it's a lot of knowledge. Let's stop it there. I know you can tell us everything, but you keep talking about coronal mass ejections.
Yeah.
These are the same as solar flares? No.
No. So these are analogous like volcanic eruptions in the sun. But these are magnetic eruptions. So these are like these noodles that are lifted. And they have very large angular extents. So you see this eruption of plasma, and there's billions and billions of tons of plasma that's released into space. It's like a giant tsunami wave that is coming toward Earth. And it can fit, many Earths inside. So Earth is like a pebble compared to this giant tsunami wave. That's a coronal mass ejection. It has the magnetic fields within it, within this cloud. It's like a giant cloud, let's say, that is coming very fast. It has a magnetic field line within it that is being stretched, that is still connected to the sun, that is stretching out like a rubber band that is being stretched. So that's CME, coronal mass ejection. You have then a geomagnetically induced geomagnetic storm, which is induced from the interaction of the arrival of the CME or solar flare with Earth's magnetic field. Because you mentioned hurricanes, I just want to, and this is rather recent, not only do active events in the sun like CMEs and the solar flares cause geomagnetic storms. What was noted actually and confirmed in 2021 is that there are also such things as space hurricanes. And the space hurricane forms in the ionosphere and then is connected to the pole through magnetic field lines. And instead of rain, it rains electrons. And it's very wide in extent with a vortex structure, so it really looks like a hurricane, but in terms of electrons and currents. And this can actually cause large currents and induce storms without any trigger from the sun itself, actually. So it's just the interaction of the solar wind with the Earth's ionosphere. So that was something new that was rather recent. So you have also geomagnetically induced currents, GICs, in the ground along very long, like rail lines, along very long pipelines. So you get these induced currents, which can rupture pipelines, which can affect oil pipelines also, affect data centers, affect trains as well. Also the power grid. The extent of the GIC's effect is related to the ground composition. So if there's a lot of conductive rocks underneath, let's say, the ground where you have these infrastructures, then you will have a stronger GIC. If the ground is different, then there might not be any effect. So it really depends on the kind of minerals and rock in the ground. These are called telluric currents, which occur in the ground based on geomagnetically induced currents.
I have one more phenomena on the list, and I don't know whether this is just a term for the same thing or not. What about the solar superstorm?
Solar superstorm, I think that would refer to like these active regions in the sun, these complexes, these coronal mass ejections. So a superstorm would be a very large active region. So active region meaning that you have a lot of these sunspots that are gathering, all and forming these very large complex. I want to remark that actually sunspots are not random. Actually, they start at the poles of the sun and they migrate toward the equator. And they form what's called a butterfly diagram over time. So they have a natural evolution as well. And each sunspot has a positive and negative polarity because of the magnetic field that comes out and goes back in. So sunspots are very interesting as well. And they can be kilometer-sized or Earth-sized or larger than Earth, Jupiter-sized. So these are very large. And they have very interesting morphologies also. Well, you had mentioned space climates, and that refers to the long-term variability of the sun.
Just like in terrestrial climate, right?
Yes. So space climates is the long-term variability of the sun, and that also reflects an amount of energy and power that's deposited onto the Earth from the sun. So there are people who monitor how much radiation is deposited on the Earth and how much is reflected back into space. Also, another interesting effect that can be is that in the future, because of pollution on Earth and because of the occurrence of geomagnetic storms, there can be increased drag on satellites. So like, for instance, SpaceX, the Starlink satellites in 2022, I think 43 or 42 of them fell back because of increased drag. That increased drag is caused by increased population of electrons in the ionosphere. So they keep these satellites, they make it harder for them to raise orbit. And then they run out of fuel and just kind of fall back down and are burnt up. And because of increased emission, there's a paper recently that shows that there can be increased, I think, spikes in drag. So it would be more difficult for future missions actually to get to orbit as they do now. So also space climate has a kind of an effect. Actually, also the burning up of satellites influences our climate as well. That's also not so much studied, but there's interest in that. And there is also studies of how space weather affects the distribution of different gases like ozone and in the troposphere. So because there is an effect also on the atmospheric gases, I think, and the neutral density. So there's also a link with Earth's climate, but that's another area too.
I hope listeners, you are now convinced that there's a lot going on that you need to read up on, because we just only scratched the surface a little bit and Carl keeps saying, and by the way this, and by the way that. There's so much to say. So the discussion will continue for sure. So I have one more question, because I have a feeling this is still not clear because we just went somewhere else. So going back, how do you actually observe space weather? Right? Because you said there are certain satellites, there is the probe, but do you have a telescope somewhere, I don't know, on the terrace, and you look at the sunspots like Galileo?
So I need to obtain a telescope one day. That would be great. There are activities where you have these Newtonian telescopes and the light comes through. And I've been in such an exercise, I think at university in New York, where the light comes through and then you can see the sunspots on paper. And that makes it very tangible, because one should not look directly at the sun. I mean, of course, even during an eclipse, one needs to wear polarized glasses. So that's one way, let's say, of light coming through a telescope, shining on a piece of paper. Because space weather is very varied, space weather, one part of it is radiation. So you need like Cherenkov detectors or other sensors that detect radiation and different types of radiation. Others, for instance, like you have the Solar and Heliophysics Observatory or the Solar Dynamics Observatory. They have different instruments. They have extreme ultraviolet instruments that look at different wavelengths of the sun. Those different wavelengths allow to probe different depths of the sun. So they can see the photosphere, they can see the chromosphere, they can see the corona. And they're at very different temperatures. So that's why the different wavelengths, one can see with different wavelengths, one can see different depths in the sun. Actually, because of magnetic heating, the corona is much hotter than expected. So all of a sudden, there are millions of degrees. The corona is very hot compared to the photosphere, the chromosphere. Also, the SOHO, let's say, has the Michelson Doppler interferometer. So it uses an interferometer, and it uses Zeeman splitting to calibrate the magnetic field strength. Because Zeeman splitting causes the electrons in atoms, like hydrogen atom, to emit light at different wavelengths. So it splits the emission. With that splitting of the emission, you can derive magnetic field strength. You can also look at polarization of light, looking at how electrons polarize synchrotron radiation or other types of polarization. There are different approaches to looking at magnetic fields, to looking at energetic particles. Yeah, also there are neutron monitors on Earth, which count neutrons, and I think they can disambiguate neutrons coming from the sun and neutrons coming from outside our galaxy or from other sources.
To prepare for the interview today, I actually watched some space weather forecasts on YouTube or somewhere. Okay. And I was wondering, where do the pictures of the sun come from? Are they computer generated? Or how do you know?
No.
This is real stuff.
Real. Okay. Yes.
I thought it was calculations and then actually rendering of...
well, there are definitely simulations like Enlil and NOAA in SWEPC, Space Weather Prediction Center.
Yeah, I visited NOAA, I think, yes.
Oh, wow. Yeah. Okay, cool. Also in the UK, there's Met Office, in India, in China, around the world. There are, I think, Australia also, New Zealand probably. It must be in South America, in Africa. There are places that monitor globally 24/7. Well, there are a couple of major stations, so that 24/7 they cover what's happening in the sun. But the images of the sun are very high resolution. So the Solar Dynamics Observatory, which was the latest mission that was launched, I think in 2017 or 2018, please don't quote me on that, but it follows up as a successor of the SOHO mission, which launched in December 1995. And that one is still active, so it's still going. But the SDO delivers much higher resolution images. And those are looking at different wavelengths at the sun. So you could really look at the sun's surface. Also like the Parker Solar Probe gives you extremely high definition images because it's just 6 million kilometers away from the sun. So it's literally flying through the solar winds that's coming off from the sun. And it's unscathed, so it's still operational. It's a brilliant design, brilliant engineering design. These are brilliant engineers that make these satellites that are able to give us this wealth of information, and also brilliant scientists that are able to process this information and make predictions. And it's wonderful. Like science is wonderful because it enables humanity to move forward. And there are also planned missions using solar sails, like the Swift mission to study space weather using a solar sail. And there's also ESA's mission to, I think, L3 in order to monitor the limb, so to catch anything that is just churning toward us. There's, as we mentioned, the helioseismology, which uses the sounding of the sun, so like quakes on the sun, so to speak, or the vibrations of the sun to study like what are possible morphologies on the side that we don't optically see. There's also a mission, I think, plans that will also, or perhaps the Parker Solar Probe is also giving glimpses of what's happening in the poles of the sun. Because the poles of the sun are actually the points that are most critical for determining the distribution of sunspots and the large-scale magnetic activity that will occur later. So everything kind of starts at the poles and then drifts toward the sun's equator. So it's vital to see what's happening there. And I think there's a mission plan to really look at the poles of the sun.
That's a lot of information. I will have a lot of work to prepare the show notes this time. But that's very good, listeners. You will have really good reference point for all the things we discussed. And Carl, thank you so much for sharing that much knowledge with us today.
Thank you, Hannah, for inviting me and for warmly hosting me here, and also for expressing interest on behalf of the listeners, on behalf of the space community in space weather. We hope that there might be a community workshop, but it would be great to gauge interest from industry or from interested people in space weather. And, because space weather affects a lot of different space assets and technology. So it's good to model or to be aware of.
Absolutely. And we'll share also some contact details for Carl if you want to talk to him directly. I'm sure he'll be happy to answer. And of course, what can I say? This is it for today. Thank you so much for listening. Remember to follow us, to support us. We are on Patreon if you want to just follow us for free, or you can also support us financially, which we obviously don't mind. Remember, you can also suggest guests there, and soon we will be expanding to Europe. So if you have some guests that are somewhere in Europe and you think we should talk to them, please let me know. This was Silex, and my name is Hanna Siemaszko.